Now we are going to focus on the memory components of the inference process. So during the LLM inference, the GPUs mainly memory are occupied by the model weights, as we have discussed. The activations of each layer, the KB cache, and also if you are using PyTorch, there are some PyTorch framework overhead. So each component has a different life cycle. Model weight will be the constants of the GPU usage, and the framework overhead permanent the residence of the memory. KB cache, on the other hand, actually grows with each token and usually kept for the entire computations and free between independent requests. And activations are temporarily freed and immediately after every forward pass. So these are the memory components, and in this section we will profile each component for the Quen 7 billion parameters, so you know exactly where every gigabyte goes. Okay, so model weights include all other parameters: the attention, Q, K, and B, the output projection matrices, and the feed-forward layer across all the 28 transformers. For the floating point precisions at the floating point precision of 16, the 7 billion parameters occupied by 14 gigabytes. And if you are going to work on this, okay, and if you are going to work on this in your project, you might want to very specifically note down the memory. So, and the weights are loaded once at startup, and the remaining resident VRAM for entire inference sections. So the cost is constant regardless of how many requests are processed. Okay. As I've mentioned, the activations are the intermediate layer outputs contributed forward pass. This actually decides growth with both batch size and the length of the input sequence. So if you are going to process, use either static batch for your inference, or dynamic continuous batch for your inference, this will actually affect the activations. So be very careful of the activations memory because it can vary a lot, quite a lot. And during inference of each activations, it can be freed immediately after the next layer inference. And next layer consumes them. So the memory footprint is much smaller and stays bounded regardless of the sequence layer. Okay, the KB cache is computed for the stores the key and value tensors computed for all the previous tokens. So in the conversations, allowing the model to attend to the task without recomputing each step. And as we have discussed, without the KB cache, generating each new token would require a full intention computation over all prior tokens, which makes the inference very slow. You might already actually felt this before. As the conversations gets longer and longer, the response time get actually slower and slower. This is due to the unavoidable cost of the inference. With KV cache, it helps this quite a lot. But even though with KV cache, there will be still a delay for long sequence inferences. Okay, so for around 500 tokens, the KV cache approximately occupies 0.3 gigabytes. Okay, so in the code, we will be profiling our large language model RAM usage. So throughout the lab, you should getting results around this range. So 3 gigabytes, around 3.8 gigabytes for the weights, around gigabytes for the vision power, and also around 2 gigabytes for the PyTorch overhead. So the vision power intentionally stays in the memory, stays in the memory in 16 floating points rather than being quantized. It is because the visual feature extractions is very sensitive to the precision loss that the language model layers. So in your project, you might want to tell the difference if you quantify too much. Will this actually affect your application or not? Okay. So how does the VRAM usage change from startup to shutdown? When the model first load, it rises the VM to from the PyTorch baseline to the whole model weights and stay steadily along as the surface is running. And during the generation, the core produced 500 tokens and the KV cache grows, so incrementally, and VRAM reaches approximately 7.9 gigabytes. So there are differences between allocated memory and reserved memory. So sometimes you might find the NVIDIA driver use more memory than your calculations. It is because it will kind of reserve a bunch of memory to for caching. So reserved memory is the large pool set aside by the PyTorch caching allocator for future allocations. So don't always require do not require frequently to call the driver. This reserved memory usually grows. So I'm not going to run the code, but you can run the code in your project. So to profile your memory, so you need to run the Python memory calculator, and you can observe the allocation memory, the reserved memory, and also free virtual RAM memory at each stage of the model loading and during the inferences. So if you pick this as your project, you need to pay attention to the difference between allocated and reserved memory and how each changes as request completes and when the session is cleared. So you need to report the peak value and the baseline after clearing and the bandwidth figure. So it's all in the script, but you need to report it in your project. Okay, so quantizations. I think you have already heard quantization multiple times in this lesson, but I want to be very specific simplify to talk about one type of quantization, which is called NF4. So essentially, quantization is a process of representing a model weights using field bits and standard 32-bit or 62-bit formats. And this trait for trading is small amount of precision for a large reduction in memory, so often faster at inference time. So the sections cover the group precision ladder from floating point 32 to 4-bit NF4, and I will try to explain why NF4 outperforms the floating quantization for neural network weights, and show the configuration code that you will be using in the lab. So NF4 is information theory theoretically optimal. So neural network weights after training for an approximately normally distributed curve. So the weights, the value of the weights is actually normally distributed and center at 0. So meaning most of the weights are very small values, near 0, and large magnitude of weights rarely occurs. So if you use the normal 4-bit quantizations, if wasted is 16 quantization level by spacing them uniformly across full metric numerical range, which concentrating too many levels, it sparks tells where the most weights actually land. So NF4 place is 16 levels positions derived from the quartiles of a standard model distribution. So every bit actually covers equal fractions of the weight mass, and maximizing precision and exactly where the weights are densest. So NF4 uses 4 bits to place those 16 values exactly where the weight distribution is densest. So keeps the detail that matter most. So the practical results, if you quantize a 7 billion parameter model using a NF4 bit quantization, it only takes half of the model weights, but only lost about 3% of quality. So this makes it fit on a consumer GPU, and not losing is full precision quality. So you can think of quantization as a kind of a waveform. So for 16-bit floating point precision, you can think of it contains all the spikes, but all these spikes cannot be actually heard by a human. If you use quantization, it's kind of smooth it out, but with total size is smaller. But when you hear the actual sound, you do not hear the actual differences. So NF4 is almost like MP3 compressions. So you compress the audio with the most important sounds without losing the quality. So smaller file, but actually preserve the quality. And here are the comparisons. So 16 level, but actually targeted for neural network usage. So here are the steps that you can quantize. So here are the head-to-head comparison for the integer 4 quantization and also the NF4. Both 4 bits, but the spacings are different. So for INT4, it is spaced uniformly, and for NF4, it's actually quartile based, so it follow the normal distributions and put all their representation of the information in the center of the normal distributions. So only use a few levels for the outliers. So in essence, it looks like this. So it put all the dense levels in the middle part, and therefore it's much better than integer form. Okay, so this NFO was introduced in 2023, specifically as an information theory optimal 4-bit format for normally distributed neural network weights. In essence, you can invent your own NF4 by sampling the weights distribution of the model, but it would be a overkill optimization. But actually, you can do this, and I think for edge devices, this might be very useful, because if you fine-tune a model with a specific weight distribution and you want to quantize it as maximum as possible, you can create your own kind of quantization format. If you are going to create your own quantization format, you kind of need to know, you kind of need to follow the steps. But I think for this course, maybe too advanced for creating your own quantization method. Okay, so as I've mentioned, there are different quantizations. The largest being floating point 32, which stores each weight in 32 bits, requiring 28 gigabytes for a model. And floating point 16 halves the memory to 14 gigabytes, but still too close for our HPC server. So I think integer 8 brings the footprint to 8 gigabytes, and technically I think it fits, but there are some headroom for activations and overhead might be sometimes might cause the out of memory errors. And 4 bits NF4 reduce the weights to 3.8, and I think this provides a comfortable margin. Okay, that's just a visualization of using NF4. So I've talked about the NF4 advantage. It cuts the cost of the memory, and here are the 16 levels of NF4. You feel free to read about what NF4 the values of NF4. So NF4 is actually same for all models, but as you can see, you can create your own quantization method of different model, because maybe some model does not follow this normal distribution curve. Maybe it's slightly off-centered. So for off-centered neural networks, you can create your own quantization method. So if you want to compare the quantization, different quantizations have the effect on the memory, you can run the code called quantization comparison for your project, and record the loading time, the peak VRAM throughout, and record the token per second generated. So you can also, in your report, write down your predictions of what format will be fastest and which will be used the least of VRAM, and then compare your prediction against the actual output. So I'm expecting for 14.60, it uses, it can produce 10 tokens per second. For the integer 8, it might produce around 6 tokens per second, and for 4-bit, it might produce 13 tokens per second. So these are the comparison method that you can try if you're working in this project. Okay, so any questions for the quantization? Okay, if there are no questions, we'll talk about the throughput, the bandwidth of the large language model inputs. So GPU throughput for large for LLM inference is not limited by the floating point operators per second, but actually by how fast the GPU can read the model weights from the VRAM. Because we are using autoregressive text generations, perform one full forward pass per token output. So every single model weights must be read from the VRAM once for every output token. So understanding the bandwidth is actually the true bottleneck that explain why the GPU that we are using in our servers is the spec of the GPU in our server is more important than the teleports rate for this workload. So during the autoregressive generation of model, it produced exactly one output token per forward pass, and each pass must traverse over 28 transformer layers using every weight matrix. So for a 7B model at 4-bit quantizations, this means transferring 3 gigabyte, around 4 gigabytes of weight from the VRAM to the compute units every single token that appears in the response. And the theoretical maximums of token per second is therefore the memory bandwidth in gigabytes per second divided by the model size in gigabytes, which is the fundamental throughput equation for large language model inferences. So in the report, please do not please specify when you are doing the calculation the bandwidth of the GPU circuit. So A16, our GPU has a rated memory bandwidth of 200 gigabytes per second per GPU unit. So the specification is actually from NVIDIA. So you can use this as a theoretical calculation. So dividing 30 gigabytes per second by the model size of 4 gigabytes, around 4 gigabytes, gives the ceiling of roughly 52 tokens per second for a single request inference on the A16 GPU. So this prediction actually matches our code. Our code, when you run the code, you'll find it's around 45 to 55 tokens per second. And if you run this code, you can get the benchmark. Okay, if you are using the different GPUs, it have a way larger bandwidth. And if you run this, you can calculate it's around 420 tokens per second. If you're running a 7B model, which is around 8 times faster. And these are the examples that you can compare with. And remember, the comparisons show that selecting inference hardware for large language model is the memory bandwidth is the primary specification to optimize. It's not the speed of the actual GPU. Of course, you might say, well, I can increase the batch size to improve the throughput because GPU can kind of overlap the memory reads from multiple requests. But the gains actually diminish quickly as more requests needs for the same bandwidth. So for batch size of 1, it achieves 52 tokens per second. But for batch size of 2, it will not double. It will only use about 68 tokens per second. So only a 0.3 gain rather than double the gain. So if you can see this this effect, you can run the Python code called throughput benchmark, and you will see our GPU results is actually with batch 1, it achieves 52 tokens per second, and with batch 2, it will have 100 tokens per second. So in summary, the T-flops measure the computation speed, how fast the memory performs, and it already has inside compute units. And the bandwidth actually measures the data speed, how fast the GPU actually read weights from the VRAM into the units. So to conclude, most of the GPU time is spent waiting for the data, not actually computing the results. So for LLM inference, as I mentioned, it requires for the GPU to load into the memory. Okay. So an analogy of comparing inference and comparing the metric of T-flops to the bandwidth is essentially T-flops refers to how fast a car you can go, and the bandwidth is essentially how wide the road you are designing. So even if you have a very fast car, if it's stuck in traffic, it will only produce a very slow throughput. However, if your bandwidth is high, you can achieve a much faster throughput. So in a much faster tokens per second output in comparison with a fast T-flops. So actually T-flops is not the rate limit, it's actually the power that the GPU can putting the weights into the memory. So when you are buying GPUs, please be aware of this. And when you heard of a data center achieves high T-flops, you need to understand what they are actually talking about. So the bandwidth is actually the critical parameter that you need to look for. Okay. So as I've mentioned, bandwidth is an important parameter that you want to compare in your project. Okay. So here is why, because when user asks for a token, the model needs to do a forward pass to predict the next word, and the weight must be loaded. And when the speed of the loading of the weight is reached, you reach a peak, so 52 tokens per second. And after this, the compute is waiting. So that's why we need another technique to speed this up, which is called batching. So with the batch size of 4, we can still read weights once, but produce 4 tokens each time it computes. So effectively, kind of maximize the throughput with the same speed of the GPU. So the bandwidth calculation, so every output token requires one full pass over the model weights. So the throughput ceiling is token per second equals the bandwidth gigabytes per second divided by the model size. And our server, we're going to divide 200 by around 4, which produce around 50. And it's the bandwidth limit. And therefore, we will be introduce techniques to kind of widen this bandwidth. So if you need to buy a GPU for your company, rank memory bandwidth first. It directly tells you how many tokens per second you can generate. T-flops dominates in training, so gradient computation is compute bound, but inference is bandwidth bound. So if you are buying a GPU for training, T-flops actually helps, but for inferencing, bandwidth is more important. So adding more compute units beyond the bandwidth ceiling yields zero throughput gain. Okay, so a practical priority is the memory bandwidth, and then the VRAM capacity, and then the T-flops. Okay, so if 2 GPU match on the bandwidth, with larger VRAM determines which bigger models it can load. So so now we are going to talk about the improvement of LLM inference speeds. So ultimately, is to increase the inference speed. You can only do 2 things: reducing the model size, so each token read will take less time, or you can increase the memory bandwidth. So the same reads take less time, and quantization from 16 floating points to 4 bits reduce the token per read. So it will speed up the inference. And for the library that we're going to introduce, which is called VLLM, optimize the maximize the utilization of available bandwidth rather than reducing what needs to be read. So together, these 2 kind of things that you can control explain all of the throughput numbers you observe in the code of this week. Okay, so I've been talking about all the essential components of doing inferences. Now we are going to a open source framework. So we will see how the VLM framework actually helps you to do inferencing. So VLLM is an open source inference engine that applies 3 core optimization. The first one is called paged attention, and the second one is called continuous batching, and the third one is called coded graphs. So using these 3, it can kind of dramatically increase the throughput on the same hardware. So no change of hardware, but you can increase the throughput. So on a A16 cluster, this optimization combined yields approximately 120 tokens per second with a 4-way tensor parallelism. So none of these optimization changed the model weights or the accuracy. They purely improved how efficient GPUs, existing bandwidth, and compute resource are utilized. And you can run the code on you can test the code before using ELM using script 3 for this week. So I assume all of you have used the Hugging Face Transformer library. It is actually designed for correctness and flexibility rather than production throughput. So it offers reserved KB cache memory. So if you try to use Hugging Face Transformer in PyTorch for inferences, you will find it extremely slow. It is actually not designed for inference, it's designed for fine-tuning and flexibility tasks. And it kind of, and another point is that traditional batching requires waiting for all the requests in a batch to complete before starting new ones, which means a single slow long complex request will block dozens of short requests from the beginning. Furthermore, Python actually incurs 50 to 100 microseconds of overhead per CUDA kernel launch. So a single LLM forward pass launches hundreds of these kernels and making the cumulative Python overhead a measurable drag on the throughput. Okay. So again, standard KV cache allocates allocation reserved maximum length memory block for every request at the start, even if most requests finish well before that length. So wasting around 60 to 80% of the space. And page attention actually divides the KV cache into small fixed page size. So typically 16 tokens each, small fixed size page, and allocates them lazily one at a time as request generates more tokens. So when a request finished, its page are immediately returned to a shared pool of reuse across other requests. So effectively raising overall KV cache utilization about 90%. So the design actually inspired by the OS virtual memory. So physical memory is divided into pages allocated on demand, and free pages are returned to the OS for reallocations to other processes. So in the context of large language model, these kind of techniques are very useful. So VRAM actually plays the role of physical memory. So this is the hard memory that you have. And fixed size KV cache blocks plays the role of pages. And VLM memory management tracks the mapping between the logical tokens positions and the physical page locations. So for every transformer decode layer, it caches 2 metrics per token, so K and V tensors, and we never recompute the prior context. So the KV cache grows linearly with sequence length, with the sequence length. And for a 7 billion model and 2,000 tokens occupies around half of gigabytes of GPU RAM per request. So serving 100 concurrent users means 40 gigabytes of KV cache alone. So before the model weights are even counted. So KV cache is actually very important idea if you are doing concurrent requests. So think of it like a kind of reporter's notebook. So every AI word is built from all the previous words. And without the cache, the model rereads the entire conversations from scratch for every single new word. So KV cache writes down a summary of every past token and it reviews it. So the model only ever process the brand new word, not the whole history as we have discussed. So this results a task will slow down with every word that stays constant speeds, no matter how long the conversation is. So like flipping a bookmark instead of reading the whole book. So KV cache are important, therefore you need to have some proper way to handle the extra memory calls. So we cannot actually just get rid of the KV cache for gaining some model size. So this is very important. And as I mentioned, it will kind of stay constant at any length. The speed will stay constant. And memory reduced, so we have to reuse the K vectors and V vectors. So instant response times. And here is the how the KV cache actually
佢可能嘅拆交，但佢冇精神。佢可能嘅拆交，但佢冇精神。
The next token will reduce the KV cache, and all subsequent tokens will repeat the same. So the speed stays flat with KV cache. And page attentions is actually essentially use KB entry stored in a fixed size page mapped with a CPU slide auth table. It's like virtual memory, and page allocated on demand and reclaimed at the moment when the moment a request is finished. So no fragmentations and no pre-reserved slab and no wasted VRAM. So you can think of KB page attention is looks something like this. So the hotel is essentially empty. The hotel is essentially your VRAM of your GPU. So if this block is reserved and other blocks are not being used, so this kind of capacity will be wasted. So page attention is actually allows the KV cache to be broken down and fit into these slots. So it is, although this part is reserved for request A, so the KV cache occupies this block of memory, but others concurrent requests can also utilize the non-used part of the memory. So it's like a page attention hotels reuse rooms at the moment the guest leaves. So the guests are the KB cache and the hotel room are the VRAM. Okay. Okay, so so the throughput is gated by how many requests fit into the VRAM simultaneously. So page attentions delivers, I think, 2 to 4 times more concurrent requests on the same hardware. This allows continuous batching. So the scheduler inserts a new request at the instance of when a page is free. rather than waiting for the entire batch to finish. So a single, say 800 GPU can reach 4,000 tokens on a 7E model, and with page attentions, PS 12,200 tokens with naive allocations. Okay, so this brings us to the differences between static batching and continuous batching. So continuous batching runs a forward pass as soon as any GPU capacity is free. And the moment one request is finished, a new one task is started without delay. In contrast with the traditional frameworks uses static batching. The server waits until the fixed size batch is full before running a forward pass and leave the GPU idle while it's waits. Okay. So combining with the page attention and continuous batching brings the GPU utilization up about 90%. So you can think of continuous batching as like a bus departing on schedule and pick up passenger at every stop at the moment one request is finished, and new ones is loaded immediately. And static batching is like wait a full group of requests ready before starting. So like the bus won't leave until all the seats is filled. So leaving GPU idle while it waits. So in practice, this can double the throughput because GPU runs nearly 100% utilization instead of waiting for the slowest request to finish before the next batch. So here is what the continuous batch is look like. It kinds of handles new requests whenever there is a space. So therefore, you can handle a concurrent request. And for static batching, it leaves a room of space behind and actually dials the GPU. So with the continuous batching, it utilizes 100% of the GPU space and limit only by the GPU capacity. So here is how continuous batching works. So the requests queue up. So multiple users send requests to the server, which are for 4 concurrent slots on the GPU. So all the batch starts with all slot fields generation begins, and the first request finished. So once request completes, say after 20 tokens, in static batching, it actually waits. So in continuous batching, the server immediately assigns the next waiting request to the slot. For the last one, affecting the speed of the inference is the Python global interlock mechanism. So means that only one thread executes the Python bytecode one at a time, and tokenization and routing schedule all completes on the same line. So when Python CPU thread is busy preparing for the next batch, the GPU sit now waiting for the next call, essentially wasting around a certain percentage of raw compute on the server. And the solution is to move the schedule to C++ and Rust, and use the sync preview to overlap the CPU and GPU work. So Using this, every time Python tells GPU to run computation, it takes, as I've said, around 50 to 100 microseconds for the next call. But a single LLM for the pass triggers around 200 such calls, and then it will be very slow. And CUDA graphs records the entire sequence of kernel launch. So essentially, with CUDA graphs, you kind of set a pre-programmed card for the GPU robot. So all the 200 steps are being recorded instead of the Python telling it move one at a time. So essentially, CUDA graphs gives the robot one memory card, not 100 sequenced instructions. Okay, so essentially the graph is compiled and CUDA freezes this recording into a graph, and simple replayable object is stored on the GPU. So finally, we are going to the tensor parallelism. We've roughly talked about how tensor parallelism can actually help to divide the load among GPU. And here we will try to kind of visualize what tensor parallelism and how tensor parallelism works in the VLLM framework. So tensor parallelism splits each weight of the matrix in a vertical manner. So it splits in a column-wise manner across multiple GPUs. So that each GPUs hold only a fraction of the model and performs its portion for each matrix multiplication independently. And at the end of each steps, and all reduced communication steps after each transformer layer, it combines the partial results adding and use the either PCIe or NVLink to do the all reduced operations. And in our four-way A16 cluster, tensor parallelism reduced per GPU memory roughly around 2 gigabytes per GPU and achieves approximately 120 tokens per second. Okay. So again, tensor parallelism divides the weights vertically first and split across multiple GPU. So on one GPU loading 7 billion parameters versus loading a 7 billion parameters across all 4 GPUs. And for the final step, we have to reduce back into 1. So it can actually fit 4 times larger models, and it parallels across all the GPUs. So fitting large model into a small GPU, this is what tensor parallelism are for, and also for the huge speed up. Okay, so here it kind of illustrates the problem. We should want to run a 30 billion parameter model in a relatively quantized in 50 gigabytes, but each GPU only has 16 gigabytes and no headroom left for the activations or KB cache. So one way is to split all the matrix vertically, and each matrix is divided into 4 kind of vertical strips, and each GPU gets one, and compute the results in parallel, and combine the results at the end. Okay. So, but the problem is you have to combine them at the end. So therefore, the combining factor becomes the bottleneck. So if you have NV link at the very end of the combinations, if it is fast, I think it is okay. Say it can perform 600 gigabytes per second versus a PCIe which only handles 32 gigabytes per second. So tensor parallelism works only if your combining link is fast rather than slow. So of course, you can split it vertically and you can split it horizontally. So essentially, you can split the matrix W column-wise and also row-wise. Okay. So actually, it looks something like this. So for tensor parallelism, and you do the matrix multiplication, but with the left side of the weights fit into GPU1 and cut the second half of the right side of the matrix for GPU2, and you do the matrix multiplication as you would did normally. So row multiplied by column, you get this one. Row multiplied by column, you get another one. And because this part does not depend on the other part, so you can split it like this, and you can combine the results together. So for row-wise, it's actually essentially the same. You cut this into top and bottom, and because the bottom half does not depend on the top part, so you can do a matrix multiplication using this chop and this chop. So you chop one. When you do the matrix multiplication, you kind of do it the row multiplied by the column, which you will get is this one, but the operation is different. So for the column-wise tensor parallelism, you actually are concatenating two matrices. However, for row-wise tensor parallelism, you are actually adding two matrices because you still need to add. So if there is no tensor parallelism for the row-wise, you actually need to kind of add the two together. Okay. So combining both steps together, you actually get the overall mechanism of tensor parallelism. Okay, so I think I will left you to read the PowerPoint slides. Well, I will continue, but I think this actually summarizes what I have talked about. So essentially, you have the VLLM framework that utilize all the techniques for production inferences. And yes, I think you can do the calculation at home because I think this should be straightforward. Okay. So you can, of course, you can do column-wise and also row-wise. Okay. So that will be quick. So monitoring. Oh, so this is actually for your project. The difference between lab prototype productions or versus the production level. So in production level, you may suffer something from like gradual VRAM drift, which essentially forcing the memory to increase. and you need to monitor the pattern and also actually decide a restart policy. Okay, so this talks about how to pick the right batch size for our deployment. I'll make it short. So if you have 1 to 5 users, you should use a batch size of 1 to 2. If you have 4 to 20 concurrent users, you need to pick a batch size of 2 to 4. If you have 20 concurrent users, you should use a batch size of 8 to 16 to maximize the GPU utilization. And you can do some experiment using the code. So this is for a voice cloning project. So combining all the techniques together, you can actually build one single application. So the pipeline actually looks like this. So Whisper, you will load a Whisper into our GPU model, and using a language model, actually vision language model for language understanding, and generate the response. And you can also clone your voice and using this text output to generate your voice. Okay, so all 3 models will be running on a single GPU, on a single 16 gigabytes GPU. Okay. So of course, the pipeline is very similar, and I'm going to skip this. And you need to measure the loading time and the response time. And also, you can try load all 3 models at once and see if you get the out of memory error. Hopefully not, because I think it is still safe to load all 3. But here are the techniques of not keeping the memory usage low. Okay. So the code is, the final code is 10 voice clone chatbot. Okay. If you choose to use this as your project, you need to actually change the code a bit, because it uses a fake image and a fake voice. Okay, so I'm going to give you some time to think about your project title within your group, and hopefully by the end of this lesson, you should come up with a project title. It is because I need to install the relevant library for your project. If you have some other kind of preference model, you need to tell me earlier for me to test in the server. Okay, so I think I will leave this part for you to read at home. And for now, I want you to actually submit, discuss within your group, and actually come up with the goals, your project title. It is because we do not have that many lessons left. So if you click into the course online, okay. So we are in here now. So we are already in week 8. And next week, we don't have a lesson. And because of actually next week's lessons count the attendance of this course. So therefore, the next week attendance actually count towards this course as well. So we have 1 lesson less. So for the week after this, I think I will put a consultations. So if you have visited the park next week, and we will, you do not have to come to the consultation. But if you have not go to the park next week, I think you have to come to the consultation. Okay. So, but you can come to the consultation anyway, if you want to. And I think it is a good point for now because there are only I think a month left for your presentation, and for this course you need to actually train some models. So we have only say 15 minutes left. So I think you can go through the final sections by yourselves. But the important part of the final sections is actually this technique. So to test for concurrent request, you might want to use Locus, a Python testing tool for concurrent request. And also, if you want to build an UI with Olama and for inference, you need to tell me in advance for me to set you up, for me to set up all the libraries for you. And there is one more thing I need to talk about before you think about your project, which is speculative decoding. So there is a clever way to kind of largely speed up the token per second, which is called speculative decoding. Essentially, it's paired a small model with a large model, and you generate the token using only the small model. But the large model is going to kind of supervise whether the small model is correct. So this improves 2 to 3 times without any change to the output quality. Okay, so three important things that I want you to take away in section 8, which is speculative decoding. Also, you might need to use a tool called Locus to test for the concurrency inferences of your project if you are working on this one. Okay. So for other slides, I will encourage you to read at home. And for now, I think I need your project title to start with. So I want you to at least start working and try to run some code to see if it runs, or do you need any extra libraries? Okay, so the project group project link is in here. And for each title, so before you leave today, you have, I think, 15 minutes left. I think you need to kind of, at least, if you cannot think of a title right now, at least you need to write down which week your group is interested in. Say, I'm interested in week 8. At least you need to write this down. If you do not have the title at this moment. So because I will be seeing you, I think I'll be seeing you next time I see you, it would be by the end of March. So it's very close to the group presentations, and because I think by then I will receive so many questions, and the server capacity because you need to actually train the model, so it is wise to train it prior to other group mates. So I think if I still do not have your group title here, you might be in a very career positions. So actually for this week, I expected a kind of a proper, I would say a proper, well-formulated project, at least by the week 9.5. Okay, so of course, if you are saying, oh, I only focus on the Git cloning, the voice cloning project, it's
要唔要
much
用呢個
simpler,
project
but
玩古天樂把
I think
聲，
we
順
still
便做
have
埋我哋嗰
to
邊？
get started early for me to kind of give some help
講到話 voice cloning
to you in
再
order for
TTS
you to kind of complete the project.
我哋都要做嘅。
Okay, that's a good start.
我哋有個本身要做嘅嘢想攞嚟做 voice cloning。